This video we are going to talk about a couple of things. We're going to talk about electrolysis a little more and looking at some of those non-spontaneous reactions. So one of the things I'm just going to touch on briefly, I'm not going to spend a lot of time on because it's one of those smaller pieces that we've kind of decided this year is just not going to be one of those major things that we're going to focus on, is electrolysis of molten salts. So why we talk about electrolysis of molten salts is when we do electrolysis, you're often going to find that water winds up either being your SOA or your SRA, simply because a lot of the ions that we use are really weak OAs and RAs. But what that also means is there are certain compounds or chemicals that I will never be able to obtain doing the electrolysis of that ion in solution. So if you think about a sodium ion, let's say, when I find a sodium ion, it's way down here in my data table. Water is here. So that means I can never purify sodium in an aqueous solution. Okay, and that holds true for anything that's below the water half reaction as a metal. I can never actually obtain that when I do electrolysis of an aqueous solution, because my SOA is always going to be water, and all of these are always going to be spectator ions. So sometimes what we do is we need to get rid of the water, right? But I can't do electrolysis of a solid ionic compound, right? I can't stick electrodes into it. I also don't get the flow of those ions to be able to complete the circuit. So instead what we do is we melt it, right? And that's why these are called molten cells, because we heat them really, really hot until that ionic compound melts. At this point, we now can stick electrodes in it, and we do now find that those ions have the ability to move around because it's a liquid. So by removing the water and melting it, what we now find is that those ions that are quite weak as OAs or RAs now actually have the potential to be the SOA or to be the SRA. And so, yeah, that's kind of how we purify those. So the downy cell is the down cell, sorry, is a really common one that we use to do the electrolysis of molten sodium chloride, because then we can get sodium metal from it and chlorine gas as well. Okay, so standard hydrogen electrode. You will notice if you look in your data booklet that the hydrogen electrode, which is kind of smack dab in the middle of your page, or hydrogen half reaction, sorry, I should say, has an E naught of 0. So why that is when they decided to determine all of these E naught values, what they basically did is they said, let's just pick something to have an E naught of 0. And then we're going to build a bunch of cells where we use that something on one side and put the other chemical on the other side. And then whatever voltage we get, we're going to say that it's entirely due to the other thing. So I don't want to say the most obvious, but I guess the comparison to something that you would be familiar with would be altitude, right? When we talk about altitude, everything is done with respect to sea level. So someone somewhere at a certain point in time decided that sea level meant an altitude of 0. And then everything else is done with respect to that. It's the same thing here. They decided the hydrogen half reaction would equal 0, and everything else is done with respect to that. Okay, normally we would spend a little bit of time talking about what happens if we change what the standard is. But again, we're deciding that that's kind of a smaller factor, and we're not going to spend a lot of time on that. But you will definitely see if you look through some questions, especially some old diplomas, and there might be a couple in some of the lessons that there are some questions about what would happen if we changed it. And I would say for this particular year to just kind of, if you really want to know, you can read into it. And if you're like, no, I'm good, then that is okay too, because we're not going to ask you about that. Big idea here is more to recognize that hydrogen was decided to be 0. Everything else is done with respect to that hydrogen value. All right, so electrolysis of water. Sorry, this picture's kind of sideways. Normally, we would go to the lab, we would do this as a demo. However, you have seen the Hoffman apparatus before. You used this back when you were in Science 10 and you did that types of chemical reactions lab. So when we do the electrolysis of water, we are basically splitting water into hydrogen and into oxygen. You will find, though, that we can't just put water inside of our apparatus. And the reason for that is it needs to have the ability to conduct electricity, right? We need to have that electrolytic conduction. And water just doesn't have enough ions on its own to be able to do that, right? The amount of hydrogen ions and hydroxide ions isn't anywhere near 1 molar, right? It's like 1 times 10 to the negative 7. So usually when we do electrolysis of water, we actually do electrolysis of like sodium sulfate or something like that. So that sodium sulfate is there as the electrolyte. When we figure out what our SOA is and our SRA is, it's water as the SOA and it's water as the SRA. So sometimes when we say that, you guys are like, well, but then nothing's happening. But if you actually look at those water half reactions, they don't produce the same products. So here's the one. It's water turning into hydrogen gas and hydroxide ions. Your other water is up here, and it's water turning into oxygen and hydrogen ions. So they are producing very different products, right? Oxygen gas, hydrogen gas are different. Hydrogen ions and hydroxide ions are also different. Okay, you'll find that when we run this and you let that gas build up, there's going to be twice as much gas on the one side as there is on the other side. And the reason for that is when we look at those equations and we make the electrons the same, right? Because we need 4 electrons and 4 electrons, there's 1 mole of oxygen for every 2 moles of hydrogen, which is why the hydrogen side has double the volume because it has twice the ratio, okay? Sometimes when we do this, we also add like bromothymol blue indicator, only because we know that the hydrogen ions are going to make it turn yellow and the hydroxide will make it turn blue. Okay, this slide covers what the next demo I would normally do is. So normally our next step would be to do the electrolysis of sodium chloride. And that's because this brings up a really important concept known as the chloride anomaly. Okay, so anomaly means something is happening that is abnormal or that shouldn't be happening. So if you think about doing the electrolysis of sodium chloride, if we listed out everything we have, right, we would be like, okay, we have a sodium ion, we have a chloride ion, and we have water. And if we went to our data booklet and we started finding the SOA and the SRA, we should find that water is the SOA and the SRA again. So we would expect that when we run this, it would look exactly the same as this one did. But what you actually find when you run it is it doesn't. So normally when we actually run this in the lab, there's next to no gas on this side, but we still have gas on this side. And the reason there's next to no gas is chlorine gas is really highly soluble. So although we see the bubbles, we usually see that we don't get a huge buildup of gas up here. There might be a little tiny buildup, but this side over here will start building, building, building all of this gas, and this side won't really have much. But we'll see that the color of this side, even without an indicator, is going to start to get a little yellowy green tint to it. And that's because chlorine gas has that yellowy tinge to it, right? That's why chlorine gas is also known as mustard gas, because of that mustard color associated with it. So when we run this, we obviously see that this doesn't look the same, which is partly how I know that it's not the same thing that happens. Okay, and when we drain this, you're going to find it smells like pool water, right? And you guys are like, oh, it smells like a pool. And that's because you guys associate the smell of chlorine as being a pool. So if you think about salt water though, right? If you pour salt into water and you were to like smell the salt water, you're not like, oh, I smell the chlorine, right? When you're at the ocean, you're not like, oh, this smells like pool. It's just like, I don't know, it just smells like outside, right? So we have an anomaly. We have something happening that does things we don't expect it to, right? So what's happening is this half reaction here is occurring, even though technically the water should be the stronger reducing agent. My data booklet tells me that water is the SRA, so I would want to pick that. But it's not actually the case. So this is kind of the only time that your data booklet, I don't want to say lies to you, but makes you think something is the SRA when it's not actually the SRA, okay? So the only time you really care about the chloride anomaly is if you're about to pick water as the SRA, you should check, do I have chloride ions? Because if I do, I'm actually going to pick that as the SRA instead. Okay, if I was picking some other thing, like, I don't know, let's say I had silver, I wouldn't even consider the chloride anomaly because I wouldn't be picking water as the SRA. But if I'm picking water as the SRA, check to see if you have chloride ions, because if you do, that's the chloride anomaly question. You need to pick that chloride ion instead of the water. Okay, there's a couple theories as to why this happens. Some of them have to do with, they think that because we used hydrogen as the standard, that's what kind of made that chlorine go in a weird spot. There are other ones that speculate that because all the other half reactions near it involve water, that there's actually a minimum overvoltage that's not included with those of about 0.25, which puts it higher. We're never going to ask you to explain. If you're really curious, you can definitely go watch some videos. But it's still kind of this unknown. We have some theories, but we haven't been able to confirm any of them. But we know it happens. We know it's a real thing. So we have to make sure that we are checking for the chloride anomaly if we are about to pick water as the SRA. Okay, if I pick water as the SRA and I don't have chloride ions listed, then I don't care about the chloride anomaly. I'm going to go with the water. It's only if I'm picking water as my SRA and I have chloride ions that I need to pick the chloride ions instead. Okay, and that's why we find that this is actually what happens when we run that cell. All right, some diploma questions for you here. So the one thing to point out when it comes to molten cells, the biggest thing that is going to change besides the fact that water isn't there is you'll notice the states are all liquids. So even though my data booklet says it's aqueous, I do want to switch that state over to liquid because it isn't actually aqueous because we have switched it to molten. The other thing you're going to find, they're not going to ask you for E-naughts of these, and that's because your entire data booklet isn't valid for molten cells, right? Your data booklet is valid for 1 molar solutions at 25 degrees. To melt an ionic compound, we are most definitely not at 25, and we are also not a 1 molar solution. We're a pure liquid, okay? So we'll do a couple of questions, and then I will leave the rest for you to kind of practice on your own. So it says, which of the following equations represents the reduction half reaction when molten aluminum oxide undergoes electrolysis? So to be reduction, it can't be A because this indicates oxidation. Same deal with C because the electrons are on the wrong side. So B and D both have electrons on the correct side. But the answer is B and not D, because look at these charges. I have 4 negatives and 4 negatives, so the charge on this side is -8. This has no charge, so it's a 0. This half reaction doesn't even work. It is not a balanced half reaction. Okay, so still talking about the electrolysis of molten aluminum oxide. So during the production of aluminum metal in the electrolytic cell, anions travel towards the, anions always travel towards the anode. And electrons travel through the, electrons always move through the wire, right? It's ions that move through the electrolyte, so that has to be D. And this, don't do this, okay? This is one of those if we change the standard electrode, and we have decided not to cover that, okay? There are some old written responses also in your note package if you want to have a look at them and try them. You should be able to answer this question. So when it was written, that kind of gave you a picture. It asks you to explain some stuff, provide some relevant balanced equations. If you choose to answer this and you want me to email you the answer, just let me know and I can email you the answer to that. And then you have this here. So this is electroplating. Okay, so I mentioned electroplating before when we were talking about inert electrodes. And I said that there was only one situation in which an inert electrode would change in mass. And that's the case of electroplating. So electroplating is a specific process where I'm going to plate a metal onto some other surface. So a lot of like coins that we use for money are actually electroplated, because then we don't have to make the entire thing out of that metal. We only have to coat the outside of it with that metal, right? The same is true like if you participate in sports and you get a medal in something. For the most part, it's just plated in that metal. It's not the entire thing. So in the case of electroplating, that would be a situation where the mass of my inert electrode would increase. And it would increase because I would be depositing a metal onto the surface of it. So that's kind of what's happening in this question, right? We have this vase, which we are trying to plate in copper. So we place it in a copper solution. And then what happens is one of our half reactions is going to turn those copper ions into solid copper. And that solid copper is going to plate the outside of the vase. So even though technically the vase is an inert electrode, the mass of it would increase because the solid copper would get deposited onto the surface of it. Okay, so electroplating is kind of that one situation where you will see that the mass of an inert electrode will increase. Any other time, the mass of an inert electrode is usually going to remain unchanged. So again, 2 parts to this question. To be able to answer question B, you will have to watch the next video, which is the Faraday's Law video, and shows you how to do all those calculations. Same as the previous question. If you do want to try solving this and you want to have a look at that answer, please send me an email and I will send you the answer to it, okay?